Please welcome to this Palabanyana Tutors Enviro. So we are going to be dealing with mass balance analysis. So with mass balance analysis, like any other concept, when we started, we need to define the concept. So mass balance analysis is also called material balance, an application of conservation of mass. So you know the definition of a conservation of mass, that mass cannot be destroyed nor what to the analysis of physical system by accounting for the material that's entering and leaving the system. A mass flow can be identified which might have been unknown or difficult to measure without this technique. So guys, that's the equation. So you can always go on internet and check a better explanation of mass balance analysis. Not that they're gonna ask you, ever they've never asked us, but you never know. And then also you can also check the definition from the textbook, whichever textbook that you use. Yes, but before we get into the concept, I want us to go through the definitions. So the steady state requires the conditions in the control volumes to remain constant, meaning that there is no change, and then as time goes on. And in simple terms, it means that there is no accumulation of mass of the material of interest. And the second one is our control volume. Our control volume is a fixed region with boundaries where the mass in and the mass out of the material of interest are identified. Non-steady state, it's just the opposite of steady state, meaning that it's not constant, that the conditions are not constant over time, and also there's an accumulation of mass. And then we have the conservative. Conservative means that there is no generation or decay of the material of interest. But non-conservative, it means that it's the opposite of conservative, meaning there is generation and there is decay. An accumulation rate, it deals with the amount of material that is already in the system at a certain point of time, and more specifically, how it changes with time. Yeah. Reaction rate is the measure of the change in concentration of the reactants or the change in the concentration of the products per time. So a reaction rate can be positive or negative depending if it's a decay or generation reaction rate. Input rate is the amount of the material of interest that enters the control volume at a certain rate, and the output rate is the amount of material of interest that leaves the control volume at a certain rate after a disturbance has occurred, and what you see. So guys, these are simple terms. This is what I define these things to be. So we move on. We find our mass balance analysis equation, universal mass balance analysis equation. Always write this in the beginning of each mass balance equation and eliminate as you go. What do I mean by eliminate as you go? Stick with me, you will see. Okay. So accumulation rate is equal to the input rate minus the output rate plus minus the reaction rate. The reaction rate is plus or minus. Why? Because the material can be decaying or generating. So yeah, and then we move on to the description of each, like accumulation, the mathematical definitions of each. We know the English definitions, the theoretical definitions, but what do mathematics say? So accumulation rate is equals to V dC dt. The V is the volume of the control volume. dC dt
is the differentiation of the
concentration of the material of interest over time. And then we have the input rate, which is C in multiplied by Q in. C in is the initial concentration of the material of interest, and Q in is the initial flow rate of the material of interest, measured in meters cubed per second, but we all know that units change all the time. It can be in decimeters cubed per minute, per hour, per year. Just make sure that your units check between your concentration and your flow rate before attempting to solve this equation. And then we have the output rate, which is the C out multiplied by the Q out. Like I said, C out will be our final concentration that leaves the control volume, and the Q out final flow rate that leaves of the material that leaves the control volume. So you can always rename this thing. Yours can be C1, C final, what, but yeah, as long as you understand then. And then guys, we go on to the reaction rate. Reaction rate is plus minus VKC to the power of n. Plus or minus, it simply denotes it's either decay or generating or both at the same time. V is the volume, K is the reaction rate coefficient. Its unit differs according to the order of the reaction. C is the final concentration. Please don't substitute the initial one. It's the final concentration. So when you are solving for the C out, just make sure that you also include this one to the power of n. N is the order of the reaction. Sorry, I wrote it in caps, but it has to be small letter. The order of the reaction. But here, guys, if you listen carefully, I mentioned that the reaction rate coefficient, its units differs according to the order of the reaction. So what was I meaning? I was meaning that when we have, okay, in mass balance, we have many orders. It can be fifth, it can be sixth, it can be 100, but in mass balance analysis, second year, Enviro, we are dealing with three orders: zero, first, and second. Ne? Sharp. So, zeroth order is equals to plus or minus VKC naught to the power of 0. Why? Because it's a zero order. So meaning that anything to the power of 0 is 1. So meaning that all in simple terms, our zeroth order is equals to plus or minus VK, volume multiplied by the reaction rate coefficient. So when it's in the zeroth order, the K unit, you're going to see it because it's in mass. It's measured in mass over volume by time. And then we go on. The other one is first order. First order is plus minus VK C to the power of 1. So 1 is first, and then V volume K, the what part. So you're going to see it that it's in first order. This one is the easiest because it is measured in one pen. It's measured in 1 over time as your K. So you know that okay, it's per time. So meaning that it's the first order reaction rate. Second order, same thing, plus minus, it's either decay or generation VKC squared from second order. So when it's in second order, the K unit is measured in volume over mass times time. So guys, I couldn't memorize this. I wrote all this on my crib sheet.
So most of the time in a question, you will be given K and you will not be told the order of the reaction, but K will be given with its relevant units. So in that case, knowing these things, knowing the relevant units of K, depending on the order of the reaction, you will be able to determine your order and then use the appropriate equations.
And then we have the mass balance cases. Interesting. So our first case is our easiest case. Oh God. Steady state conservative. So first things first, you write the universal mass balance analysis equation. Accumulation rate equals to the input rate minus the output rate plus or minus the reaction rate. Okay, so we move on. Our accumulation is 0 because it is a steady state condition, meaning that you're going to scratch out accumulation and write on top as your reason steady state. Ne? And then we go on to this, and then our reaction rate is 0 because it's a conservative condition. So meaning that we cancel out the reaction rate and write conservative. According to our definition, a steady state, no accumulation, conservative, no decay, and no generation. So meaning that we're going to be left with input rate minus output rate is equals to 0. So we know that real input rate is equals to output rate, the easiest to solve. So maybe they wanted you guys to solve for the Q or the concentration. You do your math, you get it. See? Nice one. And then we have the steady state non-conservative. Please note that sometimes they don't state to you guys that the material is non-conservative or the material is steady state or what. You just have to read and make the word talk to you and you understand. There was an accumulation. There was what. There was what. Ne? So accumulation rate, you do the same thing. You write out the universal equation, and accumulation rate is still equals to 0 because we are dealing with steady state. So you're going to cancel out accumulation rate and write steady state, and then input rate minus output rate plus minus reaction rate. So our reaction rate this time around is not 0. Why? Because it's a non-conservative, meaning that there is generation and decay. So that's how we go on. So our final equation will be 0 is equals to the input rate minus output rate plus minus the reaction rate. An example of this case is a CSTR or N to the PFR. You can go on to the textbook and read about the reactors. So PFR means plug flow reactor, and the CSTR means completely stirred reactor. I will do an example where we'll be comparing the two, which one is more effective and all that. But yeah, but please read in the textbook. And if you do not have the textbook, we go on and we have our non-steady state non-conservative. You know the drill. You write down the equation, the mass balance universal equation, and then accumulation rate is not 0 because it's a non-steady state, so we're not cancelling out accumulation rate. And our reaction rate is not 0 because it's a conservative. But our input rate and output rate is equals to 0, so which means you're going to be cancelling out input and output. So you're going to be left with accumulation rate is equals to the reaction rate. A good example of this is the CMBR, which means completely mixed batch reactor. Like I said, guys, can you please just go and read about the reactors in the textbook. So let's see. When we have a zeroth order, non-steady state, non-conservative battle, so we're going to have VDCDT. Like I said, the mathematical name for accumulation rate is VDCDT is equals to VKC to the power of naught, which is 0. So cancel out the V's. So here guys, please, it's not dt plus k. No, it's the positive k, meaning that it's a generation multiplied by dt. You get it now? Yeah. So now we integrate and then integrate, and then we get this. But if it's a decay, we will get that. Okay, moving on. So guys, this equation sometimes, yeah, this ones I think they give us, but you never know. So here we were just solving for the final concentration. I advise you guys to write them on your crib sheets because you never know. You just never know. So another one, we have the first order non-steady state non-conservative. So it's a batch. Ne? So with this one, we write down we write down the normal equation, cancel out dt is equals to positive kc. The v has already been cancelled out, and then we integrate, and then we end up getting this, and then you know which one is dk, which one is generation. So and then we have the second order non-steady state non-conservative. You do the same thing on. From here you write them out, you integrate, and then go on and go on, and then you get your final answer. We go on to our step function response. It is defined as how the concentration will change with time, when there is a sudden change in the amount of pollution entering the system. Okay, we are dealing with environmental engineering, so we are dealing with pollutions and all that. So that's why we wrote pollution. But it can always be something else. You get it? So step function response. Okay, in mass balance analysis, there's this code that always says that even if it's not a steady state condition, but just know that everything reaches steady state at some point. So a step function response kinda explains the code that says everything reaches steady state. So maybe it's a non-steady state condition we solve for the concentration, but something happens and over time, and that thing will reach steady state. So yeah, everything always reaches steady state. Ne? So yes, guys.
So basically, what we mean, or what is meant by that, is that if you are given a system and that system is not in steady state by the time, that system is non-steady. So step function response uh, tells us that as time goes, maybe over time the system will reach steady state where everything now is going to be constant, even though in the beginning it wasn't.
Here is the equation of the step function response. You can check it in the textbook, you can check it on a lecture slide. It will be the same. So export here is just e to the power of minus kd. Kd is the reaction rate coefficient, the decaying reaction rate coefficient, and kg is the reaction rate generating. So yeah, let's go straight into the mathematical descriptions. Let's go straight into the mathematical descriptions. So when we have Ct is the concentration at a certain time, and when we have C infinity is the concentration of the material in the system after it has reached steady state. So like I said, everything reaches steady state. Mhm. So we go on and we have C naught, and C naught is the initial concentration of the material in the system when time is 0. For the C infinity, guys, it takes time to reach steady state. So after like some time, and then now it reach steady state. So that's why we're saying C infinity, because we don't know the time that that material will reach steady state. Then, so other mass balance cases. So we are dealing with elementary kinetics. So guys, with elementary kinetics, it's when they give you an equation, ne, with reactants and products. So guys, it's the normal mass balance analysis question. They will not tell you exactly that water gets into the river, and then the water has maybe sodium, and then what happens to the yeah, you know, all those things. With this one, they will give it to you in a form of an equation. You will balance the equation normally the way you do it. And then the trick here for you to find out is that you must always know that the reaction rate of this reactant A is equals to negative, because the reactant is being used up. It's not, the reactant is decaying, you know. So that's why we put it in as a negative. The coefficient of the reactant in question, let's say in this case is A, it's going to be the order, it's going to give us the order of our reaction. So the coefficient of A is 2. So meaning that the reaction rate, the reaction of A, or maybe, yeah, the decay rate of A, its coefficient is 2. So meaning that the order of our reaction is 2. Now guys, but remember that it's a decay. When we're having an equation like this, we know that it's a decay because our reactants are being used up. Same thing happens to B, so we have 2B, and then, so meaning that the reaction rate of B is going to be minus K. Okay, you know that this one, is showing that it's a decay, and then this one is showing us that the coefficient of B is 2. So meaning that the order of the reaction is 2. So that's the trick behind having an equation like this. I will find a question so that I can do the example with you guys. Okay, guys, another thing that we need to pay attention to with mass balance analysis, I really don't know what's the name of this. I just call it the mixing point concept. But yeah, guys, the name, I don't know it. So we have like two scenarios. So this is our Q1, né? So there's a concentration in this. Let me just call it this M1, né? So in M1 we have our flow rate and we have our concentration is going right, and then when it gets to this point, né, another part of it is going down and the other part of it is going to the right. So this part, we call it the splitting point. So what happens at the splitting point? At the splitting point, the concentration remains the same, but what changes is the flow rate. So let's say that when it goes down with a flow rate of 1, and initially it had a flow rate of 10. So you're going to say 10 minus 1, which is going to be 9. So meaning that after this point, the flow rate of this material will change to 9, ne? And then it goes, see. So and then again, this one goes through a change here. Something happens, maybe the concentration changes and all that, and then it comes back here. So at the mixing point, because it went through a change here, the concentration of this material changed when it got here, but the flow rate changed and the concentration changed. So when it gets here at the mixing point, the concentration and the flow rate changes. So all concentrations, I don't know if this is the right word, are different in at the mixing point. Ne? It's at the mixing point, sorry. Ne? So here our Q final, which is our flow rate final, at this point when the material um, is now getting out, ne? It's going to be our flow rate at the Q final. Remember when it got here, it was 10, and then this one it became 1, the Q3 became 1, and Q2 became 9. So it goes all the way here, and then something happens to maybe the concentration here, or even the flow rate. Anything can happen. At this point, it's a change. Maybe the flow rate can change, the concentration can also change, or the concentration only can change and the flow rate remains the same, depending on the question. So as it goes, and then when it comes to the mixing point here, the flow rate at the mixing point changes, ne? And then also the concentration also changes, the Q final. Unlike when it's at the splitting point. At the splitting point, only the flow rate changes, but the concentration remains the same. So here with this diagram, the main reason for me to do this one was to explain the splitting point and the mixing point. So guys, let me give you an analogy that will help you understand this. So we have an oros, ne? And then we have a glass, ne? So we are here. So when we get here, we take the oros from the bottle, we put it in the glass. What did we do? We decreased the flow rate, or we decreased the volume, but in this case let's say flow rate because they are both in there, of the oros in the bottle, and a new one has been added to the one in the glass, ne? But if we take a sample from the bottle and a sample from the glass, and we take it to a laboratory and test to see if its concentration changed. So if its concentration, so you will see that the concentration of the oros in the glass and the concentration of the oros in the bottle, they are the same. So this is why at a splitting point, concentration does not change. Only the flow rate changes. And then we go on. So that last, we can drink the oros rosacella without putting water. Sorry. We put water. So meaning when we put water, we are disturbing again. So meaning that the concentration is going to change and also our flow rate is going to change in the glass. Ne? Because now we've diluted. Mhm. So if we take it to the lab, the diluted juice, and then with that one, we will see that the concentrations are not the same. So we move. When we get to the mixing point, we take the bottle, yeah, the one that has Oros, and we mix that one with the juice, with the diluted Oros in the glass, and then we mix them. When we mix them, we will notice that the flow rate has now changed and the concentration has now changed. So this is how the splitting point and the mixing point concept works. I will do an example on this, you'll get to understand. But I hope you grabbed it and you understood. So let's talk about the flow rate at this part, how we get it, because normally they don't give us the flow rate. So how we get the flow rate at this part? The flow rate at this part, the final flow rate is going to be the sum of the flow rate after the disturbance has occurred and this plus the flow rate of the material after it has passed the splitting point. So we add them and then we get our flow rates. See? Yep.
So you will find that in a stream we have different materials. So mass fraction is the percentage of components within the stream. So let's say, as you can see, we have A and B, component A and B. So a mass fraction is the percentage of that component within that stream. So in that stream, if we have different components or materials flowing in that stream, they have to add up to 100%.
This concept with the aid of an example because the English is gonna run away and everyone is going to get confused. Okay, I will do an example on this. This one I promise you, so that you get to understand because I can't explain it without an aid of an example. So, okay, guys, that's all I have on mass balance analysis. I will meet you guys again when we're doing the examples. Please tune in. Thank you so much. Don't forget to like, subscribe, comment below what I left out or what you would like us to cover and all that. Thank you so much. And also, guys, please visit the link, the Telegram link. It's very helpful. We send our tutorials there that are solved and all that. You know, we can't make long videos. So obviously, some of the tutorials we wrote them down during our time, took them pictures, and then we're gonna send them um, on the Telegram group. So please visit that and do so. And if you do not have the textbook, please, I'm gonna send the textbook and its memo. Okay, is it correct? Yeah, it's memo to the group. And another textbook that I like, it's called Mitch. I can't pronounce his name, but yeah, that one. All right, guys, see you. Thank you. Bye.